First, integrated circuits have evolved from a few transistors to millions, driven by the needs for high performance and lower cost. Secondly, semiconductor libraries provide optimized standard cells, reducing design time and cost, allowing for greater innovation. Next, low power, high-speed cell improve efficiency and extend battery life in portable and IoT device. Lastly, GDI use fewer transistors than CMOS, reducing power consumption and area, ideal for power and space-constrained application.
Next, tools used for analysis and integration. First, Virtuoso, a tool for custom IC design including schematics, layout, and initial simulations. Second, Genus, used for high-level synthesis and generating gate-level representations. Third, Innovus, handle physical design, placement, routing, and optimization. Fourth, Quantus, perform parasitic extraction for accurate modeling of interconnects. And lastly, Voltus, provide power integrity analysis and optimization, ensuring robust power distributions and minimizing power loss.
I will explain the part for introduction. Firstly, let's talk about modern integrated circuit or ICs. They are a cornerstone of energy-efficient electronics, which is crucial in today's world. The building blocks of these circuits include logic gates, flip-flops, and multiplexers. Together, these components are key to enhancing the efficiency and extending the battery life, which is particularly important for devices we carry around, like smartphones. Now, powering these ICs, we deal with different types of power, which is dynamic power is consumed when we reach the capacitive loads. Static power, on the other hand, is due to leakage currents when the device is idle. Think of it like a dripping faucet. And short-circuit power occurs briefly when transistors switch. Next, to ensure we get robust performance, we need to characterize our standard cells well. We test them across different process, voltage, and temperature conditions. We also seamlessly integrate these designs into larger systems using advanced tools like Genus and Innovus, which help meet our performance, power, and area targets, often abbreviated as PPE. The process we use is meticulous, combining our technical know-how with sophisticated software solutions. This approach is essential for creating efficient and reliable products. And lastly, it's not just about making better electronics, it is also about addressing broader needs like meeting stringent power requirements, prolonging battery life, and reducing overall energy consumption.
Assalamualaikum and welcome. My name is Abdul Farmi. Today, I will demonstrate the simulation of designing a circuit using Cadence Virtuoso. Let's begin. First, we will start by opening the VMware software. Please allow a few seconds for it to load. Once VMware is active, we will proceed by opening a terminal window where we will enter the necessary command to launch the Cadence Virtuoso. After launching the Cadence, our next step is to create a new file to save our project. This will allow us to begin the design process. In today, we will focus on three main steps. First, designing a GDI engine in the schematic diagram. Second, obtaining the transient response result. And lastly, designing the layout followed by conducting check and running the RC, LVS, layout versus schematic, and RCS analyze. I will guide you through each step to ensure you understand how to design a GDI engine effectively.
methodology to design a circuit using Cadence Virtuoso, the process begins with installing the Cadence Virtuoso software. Once installed, a new library and cell are created to organize the design files systematically. The schematic is designed using PMOS 1V and NMOS 1V transistors. Following this, CMOS inverters and NAND gates are constructed within the schematic editor. The schematic is then extracted to generate a netlist and perform necessary checks to ensure design correctness. The layout is generated and floor planning is performed to optimize the placement of components. After floor planning, global and detailed routing is conducted to establish accurate connections between components. This involves defining precise paths for electrical signals to travel through the layout. Once routing is complete, the design undergoes verification through Design Rule Check DRC to ensure adherence to specified design rules and constraints. If the DRC check passes, the design process is complete. If the DRC check fails, troubleshooting is necessary to identify and correct any errors or violations in the design. Upon successful verification of all checks, the design is finalized.
The GDI technique simplifies circuit configuration by using fewer transistors, as depicted in the diagram on the right. This streamlined approach not only reduces the complexity of the design, but also leads to several key advantages. First and foremost, GDI significantly reduces power consumption. This is a critical factor in the design of modern electronics, where energy efficiency is essential. By minimizing the number of transistors, the GDI circuits consume less power, making them ideal for battery-operated devices and energy-sensitive applications. Firstly, we validated the operation of GDI and gate. Our simulation demonstrated efficient performance in terms of both power consumption and speed. Next, we conduct a series of checks on the layout of the GDI AND gate. We started with Design Rule Check (DRC) to ensure that the layout adhered to the necessary fabrication rules. The result showed that our design passed all the DRC checks successfully. Following this, we performed a layout versus schematic (LVS) verification. This step ensures that the layout corresponds accurately to the intended schematic design. Our result indicates a perfect match, confirming the integrity of our design. We also carry out resistant-capacitance extraction (RCX). This process provides an accurate model of the parasitic elements within the circuit, which are crucial for understanding the real-world performance of the design. The RCX results were within acceptable limits, indicating minimal parasitic impact. Finally, we compared the transient response waveform of the schematic with that of the layout. This comparison is critical to ensure that the dynamic performance of the layout mirrors that of the schematic. Our result shows that the transient response will closely align, validating the accuracy of our layout implementation.
Designing and simulating low-power standard cells using Cadence Virtuoso software offers several advantages. First, Virtuoso offers a comprehensive tool suite for schematic design, layout, simulation, and analysis. Secondly, the software allows designers to work at the transistor level, offering the fine-grained control over the circuit design. Lastly, Virtuoso supports various power optimization techniques to help designers achieve significant power saving. However, there are also several disadvantages. First, software complexity, which can be hard for new users. They need a lot of training and practice to use it well. Next, high computational demands for running simulations and optimizations. Moreover, the cost of commercial license for Cadence Virtuoso software can be too high for individual designers or small companies, it making hard for some users to access the software. Lastly, multiple design iterations required, which make the design process longer and delays the product release. In conclusion, Cadence tool provide robust framework for low-power standard cell design, and integrated approach ensures efficient and reliable designs. Despite the challenge in modern IC design, these tools are invaluable, helping designers create effective and energy-efficient solutions.